Okay, so I will attempt to divert you from the noise outside and tell you about experimental dynamos. And I come at this from a very different point of view, I think, from most of the other speakers that you've been listening to. I'm not a mathematician, and when I use computation, it's because I want to get an answer. Not because I'm concerned about the numerics so much, although I do care about those things. And I'm very much a physicist. And in physics, one of the legs of physics is experimental work. And experiments complement observation. Observation is only part of the story. And so I try to bring that perspective to dynamos. So I'll be talking about so many dynamos. I don't know if you've seen this before, but this phrase spelled backwards is the same phrase. It's a palindrome. And here's the experimentalist in the lab. And these objects here are all dynamos. They're electrical generators, continuously converting mechanical energy into electric energy. But of course, we're thinking about other dynamos. And what I'll try and do in this lecture is go through, well, I'll tell you about this in a second. I'm going to try and connect the experiments in some ways to things that we believe are important for all of these astrophysical objects. So this is, we know planets have magnetic fields that are generated by dynamos. Stars have magnetic fields. Pulsars have magnetic fields. This might be quite a different one. Galaxies, accretion disks, and maybe even clusters of galaxies. All these things have dynamos. Everywhere we look in the universe, we see plasma. It's magnetized. The reason we see things usually is because we have radio telescopes that can observe synchrotron emission that's there because there's a magnetic field present. And so much of modern day astronomy is linked to the fact that there are magnetic fields everywhere. So what are dynamos? You know about this, so I'm going to repeat just a little bit of what you had this morning, but these are systems that continuously convert kinetic energy of flow into magnetic energy. And Emmanuel talked about the disk dynamo, and that's fine, so I don't have to go through it. What I would like to call your attention to, because we'll just keep talking, and you know what this number is already, the induction equation has this nice property that you have this linear term where there's a prefactor, and if it's greater than 0, it's a growing system. If it's less than 0, it's a damped system. And if you combine these parameters, first of all, it's dimensionless. This combination of parameters is dimensional. Okay? Yeah, great. If you combine these parameters together and you work out what the units are, it's the product of a magnetic, the inverse magnetic diffusivity times the size times the velocity, which is the magnetic Reynolds number. So the magnetic Reynolds number already enters in directly to this equation. And this just says if this thing, which is a magnetic Reynolds number, is bigger than 1, the system becomes a dynamo and it self-excites. And if you haven't seen a picture of it, you can go to the Deutsche Museum in Munich, and you can actually see the first self-excited dynamo that was built by Siemens in the mid-1800s. And this is where the term self-excited dynamo comes from. And this was the thing that Larmor was referring to when he, when he wrote his seminal paper. So the idea of creating a disk dynamo is very, very hard to realize in the lab. So if you go back to, if you actually try and design this, you'd look at this geometry and you'd think, that's not so hard. I should be able to take this, get a nice big chunk of copper, some wire, and actually create this. It's not that hard, it's not that difficult of a geometry. But it turns out for copper, it's very, very hard to get the conductivity low enough for this system to actually be constructible. When people build this, they have to add amplifiers in to make this work in practice. And so the way that Siemens did it was by using ferromagnetic materials to control where the magnetic field went inside this object. He uses insulators around conducting wires to control which pattern the current goes into. And he has a mechanical system that controls the velocity in a very specific way. So the challenge for us as MHD physicists is to take this object and heat it up to 2,000 degrees where it melts and all the insulators are wiped away and the iron loses its ferromagnetism, and still ask the question, can we stir this thing in some way that still gives a self-excited magnetic field? And that's, of course, much more complicated. So this is a big challenge. And the way I'm going to give this talk is I'm going to talk about theory to begin with, or at least what I refer to as theory. And I'll give it from the point of view of telling you about buildable dynamos. So buildable dynamos are things that you could actually construct in the lab. And I'm doing this from a theoretical point of view just to illustrate the concepts that we'll be using to make a dynamo and try to give you some intuition there. Then I'll talk about astrophysical dynamos because I'd like you to see the context in which the experimental physics results may feed back into the astrophysics and solar physics and geophysics community, because there are things we're learning in these now which can inform the astronomers in some way. And during the last decade and a half or so, people have been working with using liquid metal experiments, and there have been some successes there. It's not a perfectly successful field. Liquid metal experiments are flawed in some ways. And we're just embarking on plasma dynamos, which are also not perfect creatures, but we think that they have the promise of going into areas where liquid metal experiments haven't been. And so, again, throughout this, the philosophy of this talk is very much that of a physicist. What I can't create, I don't understand. And if we really understand something, we should be able to produce it in the lab. At a minimum, we should be able to do a Gedanken experiment where we think about how we would construct something. And then I promise you, if you actually try and build one of these things, you're going to learn things that you didn't anticipate. And that's the experimental method which makes our field physics. Okay, so this, of course, is review also, and that's why I'm going through it quickly. We start with the magnetic induction equation, and we have a magnetic Reynolds number. Dynamos are going to operate in a regime, experimental dynamos are going to operate in a regime where Rm is big. It's going to have some minimum value, some critical value above which we look at the systems become dynamos. And the tricky part is going to be figuring out what velocity field is a useful velocity field for creating a dynamo in the lab. This plus boundary conditions plus some scaling of the magnetic Reynolds number is going to set the parameters for the experiment. The equation of motion, and I'd like to talk about two limits, and I come at this from the plasma physics point of view, and so this may be a little bit particular. In the equation of motion, which is just the Navier-Stokes equation plus the induction term, we can think about two limits for this. If I was working in fusion plasmas, I would think about a system which is completely dominated by the Lorentz force, and that would be a flow-dominated or a magnetically dominated regime. And in the magnetically dominated regime, magnetic field lines which have tension can be plucked and they restore themselves to their original position and Alfvén waves propagate. That's one limit. The limit that we're more interested in from the standpoint of dynamos is to work in a regime in which the Lorentz force, at least initially, is very small. So the equation of motion doesn't have the Lorentz force in it. We'll talk about that as the kinematic limit. And we'll solve the equation of motion to figure out what velocity fields exist and then can be generated given boundary conditions. And then work our way backwards to see whether or not it's a dynamo. And then perhaps get into the nonlinearities to look at things like saturation. So this flow-dominated regime is the condition that inertial forces are bigger than the magnetic forces. And this works out to be that the velocity of your fluid is bigger than the characteristic Alfvén speed, where the Alfvén speed is the same Alfvén speed you have in the magnetically dominated regime. So if we want to do experiments using plasma, we'll want to do them without with a very small magnetic field. In plasmas, it'll turn out also that that's a little bit incompatible with making the magnetic Reynolds number big. And the reason is, well, I'll come back to that. Okay, so this regime, large magnetic Reynolds number and high Alfvén Mach number, or flow dominated, gives you this, this very important, I call it the fundamental tenet of plasma astrophysics, which is that field lines can be stretched by flow. So if we start, for example, with some seed fields that are just like this, and we start to move the fluid to the right in this region, we can think about when the magnetic Reynolds number is big, the field lines are frozen into the moving fluid. And because the Lorentz force is small, the field line tension can't pull it back. The inertia is able to carry the field lines with it and stretch the field lines. And so what happens is when you take a seed field and act on it with some sheared velocity, the magnetic field gets stretched out into this, this type of configuration. And if you let it go for a long time, the magnetic field in this direction can become very, very big. What stops it from growing? What's that? So the Lorentz force could stop it from growing. Another thing that could stop it from growing would be magnetic diffusion. So if the magnetic Reynolds number is not too big, it may reach some resistive diffusive state, or the Lorentz force is going to change the flow. Either one of those is possible. Okay. I can't hear you very well. You'll have, okay. So in a astrophysical object like a star or a galaxy, there's almost always some sort of large-scale axisymmetric shear. And I'm just going to give you pictures. This is eye candy. It's stuff that you've already heard about. But the idea is, field lines stretching in some astrophysical object, would proceed like this. You might start with a magnetic field which was pointing in the north-south direction. And if you have some differential rotation, you're going to wind up where the center is rotating more rapidly than the outside of the fluid. You're going to wind this system up so that it creates a very strong east-west magnetic field, if you will, from the dipolar field that you start with. And so you can ask, is something like this a dynamo? We heard an anti-dynamo theorem this morning. Is this a dynamo? We're certainly creating magnetic energy from kinetic energy, so that part is satisfied. But there's one more part of it, which is that you need this positive feedback, which allows the original seed field to be regenerated from the strong field that you're producing in this case. And that's part of the story as well. Okay, so just to summarize that part, we want to have, in an experiment, we're going to be looking for experiments that have big, hopefully as big as possible magnetic Reynolds numbers, and we're going to want them to be in a flow-dominated regime. And this, it turns out, has been completely unexplored by plasma effects, by plasma experiments. And the reason is, in plasmas, the conductivity depends on the electron temperature. And the electron temperature, we want it to be high. So unlike a metal, a liquid metal, when the temperature of a metal goes up, the resistivity increases. In a plasma, when the temperature goes up, the conductivity increases. To make a very conducting plasma and make the magnetic Reynolds number big, you want a very hot plasma. To make a hot plasma in the lab requires some form of thermal insulation. And if we do this in a normal fusion or in a normal plasma physics context, that requires magnetic fields to provide the confinement. So normally we make magnetic buckets, tokamaks or something like that, to provide the thermal insulation that allows the plasma to become hot. And that violates the second condition. So this is a really unexplored territory for plasma experiments. It's also not easy to stir plasma, as it turns out. We had to invent some techniques to make the plasma spin, and we'll talk about that. Okay, so now buildable.
Is essentiality of the second condition, because we know that in MHD turbulence often the magnetic energy becomes comparable to kinetic energy, and then this parameter would be 1.
Of order 1.
So certainly,
at a minimum, it comes from very high down to 1 in the saturation phase.
So for laboratory experiments, it's not possible to achieve a dynamo where this parameter is 1. Why are you making this demand that this parameter has to be much larger than 1?
Well, ideally you'd start with no magnetic field at all.
Yes.
The Alfvén speed would be 0.
That's right.
And so it starts out at infinite.
Yes.
You'd like to begin in that regime.
Yes.
So that's basically the point.
Okay.
Okay, so you want to start with no magnetic field and watch it come up.
Start with that, but eventually, do you want this condition to be
No. I mean, well, when it saturates, you want to study that.
Okay.
Yes, that's interesting. But this is very much in conflict with most plasma experiments. Okay. So how would we build a dynamo in the lab that might be interesting? So I'm going to show you a flow that's been used in at least 3 experiments as an attempt to make a dynamo. And this is, we'll call it a 2-vortex flow. And it comes by other names. You can make this with a von Karman geometry in which is 2 counter-rotating disks at the end of a cylinder, or it goes by a name of Dudley and James's flow because they were the first people to study it. But I'll just call it a 2-vortex flow because it's 2 vortices packed inside a sphere, okay? And the idea is you can imagine making this flow with 2 counter-rotating propellers, okay, that provide thrust out along the axes. So these are propellers that are driving flow out, and they're also, they inject helicity to the flow because they're spinning, okay? And if you trace out the trajectories of fluid elements, they basically would trace out surfaces on 2 tori, which are inside this sphere, okay? And this flow, if you choose the flow to be this, it makes this magnetic field if the magnetic Reynolds number is big enough. So this is a magnetic field which is transverse to the axis of symmetry for the flow. So this is the axis of symmetry for the flow. It's symmetric about, okay. Yeah. Is it okay? As high as possible? You weren't getting enough? Okay. Okay. So, how does this dynamo work? And what are its dependencies on magnetic Reynolds numbers and so forth? So this flow...
You have to have a symmetry breaking because
yes.
it's symmetric about the axis.
Yes, does. So does this satisfy Cowling's theorem? Does it violate Cowling's theorem? So the form of Cowling's, I'll mention it again, the form of Cowling's theorem that Emmanuel quoted said, when flows are symmetric about an axis and the magnetic field is symmetric about the same axis, a dynamo doesn't exist. And this, go ahead. It violates? Does not. And why not? Magnetic field is not axisymmetric about the same axis. They don't share the same symmetry axis. So this is perfectly fine. It's an acceptable dynamo solution. And you can kind of imagine this as the simplest building block for some sort of spherical convecting object, right? Because what you really have is, if this was the center of a star, say, this is one upward welling plume of convection going out along each axis as it rises up and then falls back to the equator. This is kind of the simplest and largest convective cell system that you could imagine putting into a sphere. It's not the way stars work, but it kind of captures some of that physics. Okay, so if you will, helicity and something like the alpha effect, you can almost imagine this having that. Okay, so let me give you an idea of how this works in practice. So the idea is, let's imagine I have a fluid which is very highly conducting, so the magnetic field lines are frozen into the moving fluid. And I'll have these propellers spinning, so they're providing thrust out along the poles, twisting and stretching the field lines, which is amplification. And you can ask what happens. So what happens for this geometry is this seed field, which is initially down, it gets pulled out by the axial flow. And then because of the twist of the propellers, the field line which is coming down here gets pulled back up around the outside. And then it gets laid back down in exactly the right spot in the middle to reinforce the central part, right? And that's the positive feedback that we're experiencing with the microphone. I mean, that's that geometry is there. So sometimes people refer to this as a stretch, which is amplification, twist, and fold like dynamo. And in the end, if you let this go forever, and if you assume that the magnetic fields are frozen perfectly into the fluid and don't diffuse at all, it turns out this isn't a dynamo, but you can see, and that's because inside here you have lots of field lines which are one going one way, one going the other way. Some sort of diffusion is necessary to smooth this out and make it look like the picture I showed you. In fact, quite a bit of diffusion is necessary. And for that reason, well, I'll explain that more in a second, but the point is some sort of reconnection of these field lines, something needs to happen to smooth it out and make it work. So if you look at that, if you look at the magnetic eigenmode for that case that I just showed you, and so I'm not going to show you how I solve the equations. I'm just going to tell you that if you start, so the magnetic Reynolds number characterizes the speed of the flow. If I start with some material like a plasma at a given temperature or liquid sodium, it has a fixed conductivity. And so the magnetic Reynolds number is like the velocity. As I turn the velocity up from 0 to 100, whatever units you want, the growth rate for that magnetic eigenmode starts out less than 0, damped, and it becomes less and less damped, and there's a critical point above which this system has a positive growth rate. And so this is the same as that circuit equation where I have a parameter that goes from less than 0 to greater than 0, and up here is where we have a dynamo. And it illustrates the idea that the magnetic Reynolds number, there's some critical magnetic Reynolds number that you need to have built into your experiment to make it function as an experiment. And that oftentimes is the hardest part, is getting the magnetic Reynolds number up high enough so that you have an interesting experiment. Okay? Now this dynamo has, okay, so if you take something like liquid sodium, which is very conducting, it's the best conducting metal that we know of, and you put it in a sphere which is a half a meter in radius, so a meter in diameter or something like this, you can work out the dimensions. It works out that the magnetic Reynolds number is something like 6 times the flow speed of the sodium in meters per second. So if I make a flow speed of 10 meters per second, I would have a magnetic Reynolds number of about 60, which is, this is doable. It takes hundreds of kilowatts of power to do that, to get 10 meters per second or more. And correspondingly, we're just barely able to get above the critical magnetic Reynolds number in liquid sodium experiments, but it can be done. You can sort of operate in and around this regime and study the onset of dynamos, okay, using liquid sodium. What would happen if you went to even bigger magnetic Reynolds number? In this case, this is what happens. The growth rate for this eigenmode actually maxes out, and then it drops back down to 0 and becomes damped up in this region. Okay? Might be that there's another one which turns on up here, but this is a really interesting thing. Remember, I told you that a little bit of resistive diffusion was necessary to make that magnetic field in the center sort of smooth itself out. Well, that's what's showing up here. If you let If the field is perfectly frozen into the moving fluid and there's no chance for the topology to change, you don't get a dynamo in this case. Okay? This is a characteristic of a type of dynamo that we call a slow dynamo. A slow dynamo is a dynamo that depends upon resistivity. You can't make it too conducting or it goes away. Okay? So that's a lesson. Okay? So building the dynamo I just showed you is straightforward with a liquid, like liquid sodium. I can put two propellers inside a sphere and I can rotate them and they can drive the flow, and mechanically you can see how that's done. If we want to do something with a plasma, it gets a little bit more complicated. So I'm going to add a little sophistication now and think about how we might do this.
So one question about this setup. So I suppose you will have a degeneracy in the sense that whether magnetic field will this way or that way, the energies will be the same for all the configuration. So in such a situation, experimentally do you find magnetic configuration to be stable or did some change?
We'll come to that. I'll show some observations that talk about reversals and things along those lines. Okay, yeah. It's nice and quiet now. This is good. This is great. Okay, so if we're talking about buildable dynamos, I'm gonna tell you what I think we can do with plasmas that's a little different than with sodium. And that is, in plasma, we've invented a technique for holding a plasma and stirring it on the boundary using some special techniques that I'll explain when we get to that part of the talk. The point at this point is only that we can control what the rotation is as a function of latitude. I have a technique that works for controlling what the rotation is on the boundary of a simply connected plasma. Okay? So the thing I just showed you had a big propeller in the middle of it. This flow is driven from the boundary. Okay? If you know what the boundary conditions on a simple domain are, and you know what the Reynolds number is, you can solve the Navier-Stokes equation in the inside, and there's a well-defined solution to the Navier-Stokes equation which gives you the total velocity field. So if I impose this boundary condition on the surface, and I have zero slip boundary conditions over here, this is the self-consistent field that develops. There's diffusion of the magnetic field in, or the velocity field in from this boundary. That's through viscosity. There's also a centrifugal force which develops because the poles are rotating and they throw plasma out to develop this poloidal circulation. Okay? So this gives a two-vortex flow very similar to the one that I developed using the propeller. Okay? But it's driven from the boundary, and this is what we think we can do with plasma. And this is probably buildable as well. So if we're studying boundary-driven flows, the way we've specified this problem to figure out how we might approach it, we solve the steady-state Navier-Stokes equation, varying the fluid Reynolds number, and that gives a solution which looks like this. Okay? Then what we can do, it's still symmetric. It doesn't yet break up. You'll see that these are very small fluid Reynolds numbers, like several hundred only. That you need that to get the momentum to diffuse inward, it turns out.
So to get this sort of flow, don't you have a forcing gun?
I do. I'm driving the flow at the boundary.
Oh.
Yes, I mean, it's like, I mean, if you would do a fluid experiment in a rotating tank, and you start initially with a stationary fluid, and you start to spin, the momentum comes in from the boundary, right? That's the way to think about it. But I'm doing one more thing here which the fluid experiments can't do, which is I can control, as a function of latitude, what that bit should be. So I can make it spin one way here and the other direction here. You might do this with two disks. That would be von Karman-like drive. But I can do this differentially, it turns out. Okay? And that's kind of neat. So that's what we're.
Essentially, it's the boundary conditions which will drive the flow, so you don't have to have a forcing turn
on the inside, exactly. But we're limited by the type of flows we can develop. This is it. I mean, this is it's this kind of two vortex flow that we can get.
Except from the experimental techniques, what is the difference between the liquid metal and plasma? Except for the experimental techniques.
So many things. I'll tell you all about that. Yep. And there's so many good. Don't stop asking questions. This is good. I'll describe all of that. Yeah, that's where we're heading. Okay. So the first step is to solve the Navier-Stokes equation to develop a scenario for a dynamo. Then we solve the kinematic induction equation, which is to find the growth rate for the least damped magnetic eigenmode. This is linear in B, where you're given what the velocity field is. This is the velocity field, which is self-consistent solution to the Navier-Stokes equation. And it depends upon the magnetic Reynolds number. And this will, and so what you end up with for this particular thing, so this is a fluid Reynolds number of 300. This has a magnetic Reynolds number dependence for the growth rate. It comes up, it's a slow dynamo, it turns over and comes back down. It has a critical magnetic Reynolds number of about 300, and it turns off at about 650. Okay? And that's, well, it's significantly above what we can do with liquid metal experiments, but it'll turn out that plasmas are not so hard. Okay? And this also has, now I've changed axes on you. This has a dipole moment which is transverse to the axis of symmetry, which was running vertical. So I flipped everything on you here, but this is what we have. So this dependence on the fluid Reynolds number, it turns out, is pretty significant. So if you start out with a very viscous fluid and the Reynolds number is low, you get no poloidal circulation. You just get toroidal rotation about the axis that diffuses in very effectively because the viscosity is enormous. As you increase the fluid Reynolds number, decrease the viscosity, you start to develop the poloidal circulation. And as you go to higher and higher fluid Reynolds number, the poloidal circulation gets even bigger. And so this is actually a plot of the poloidal to toroidal being around the axis. This is the poloidal. And it actually just goes up and up as you increase the fluid Reynolds number. So remember, the amount of stretching and twisting was just critical in the picture I showed you. We had to take the field line, which was coming down the middle, wrap it back up around the outside, and lay it back down in just the right way. So the poloidal flow was critical for this dynamo. And it turns out this doesn't work below a fluid Reynolds number of about 100. And the details of the flow matter. So in this region, the critical magnetic Reynolds number for each of these flows gives a curve that looks something like this. So the fluid Reynolds number matters, and the magnetic Reynolds number matters. Okay? And the plasma parameters matter. This is sort of a punchline also, and I'll show you that these plasma parameters that get here are relatively straightforward to do in the lab. Okay? Okay.
What happens to higher Reynolds numbers?
Higher magnetic Reynolds numbers? So I stop here because our first fluid instability, our first non-axisymmetric fluid instability starts to set in. I'll show you simulations later about the transition to turbulence. Yeah, by the way, everything I'm showing you is basically, I'll show you data from plasma experiments. We're doing plasma hydrodynamics at this point. We're stirring plasma, studying how the flows develop. And this is a relatively new area. People haven't done experiments on hydrodynamics without magnetic fields, I think, before this. Lasers can do this, but laser-produced plasmas, those are very impulsive and not sort of the steady state-like experiments. Okay.
So here flows remain laminar.
So far laminar, yep. Okay, so I'm using this term slow dynamo. Slow dynamos are dynamos in which the growth rate goes up and then drops off and actually goes away when you go to very large magnetic Reynolds numbers. It can be like this. You might have a dynamo that sets in here or here, but eventually the growth rates go away. So if you make the system very highly conducting, a superconductor if you will, or very big, like a galaxy, or like a star even, magnetic Reynolds numbers are enormous. It's very hard to understand how slow dynamos could work in stars or galaxies. Maybe slow dynamos are just fine for planets, okay, where the magnetic Reynolds number is not too big. But there's another type of dynamo, and you've heard about this. They're fluctuation dynamos, which oftentimes work in the limit that the magnetic Reynolds number gets very big, okay? And because astrophysical systems are always have enormous magnetic Reynolds numbers, we're concerned about how fast dynamos might evolve also. So could one build a fast dynamo in the lab? And I'll show you an example of one that we've conceived. And the idea is to take the flow that I showed you, where I'm controlling the rotation in this hemisphere and this hemisphere, rotating one way here, the other way here. And now I'm going to add some time dependence to the flow by sloshing it at the equator. I'm going to force it one way and then back. I'm going to go back and forth. So I'm reinforcing either this hemisphere or this hemisphere, okay? And this is a very low fluid Reynolds number. It's a very viscous. You'll see there's very little structure in the flow. There's lots of viscosity. If you do this flow, and you'll see how it works here, this is what the flow does. It sloshes between one hemisphere and the other, okay? And so you get this sense that there are two vortices going up and down. And then you could ask a question like the following. What if you were to sit on a fluid element and you followed that fluid element, would you be tracking out a curve that looks like this? Would there be a closed torus on which that fluid element sits? And it'll turn out that this flow has the property that the fluid trajectories are chaotic, okay? And what I mean by that is if you start out with no sloshing and you traced out the fluid elements would simply sit on one torus, like those streamlines I showed you earlier, okay? But as I turn the sloshing up, I start to go back and forth and I make this system wobble up and down, and I trace out fluid elements, the particles start to go everywhere inside the sphere. If you start out with two fluid elements which are close to each other, and you trace them, they exponentially diverge away from each other. They have a finite Lyapunov exponent. The flow is chaotic. And I'm making this chaos with very smooth laminar flows, okay? If a field line connects those 2 points that are being exponentially pulled away from each other, magnetic field is going to grow. And this gives rise to a small scale dynamo. If you look at, yes?
What is the Lyapunov exponent? Have you measured?
We have, and I have no idea, I can't remember. Yeah, but it's...
I'm trying to understand how fast it is diverging.
Yeah. The paper has this in it, yep. But this is what the magnetic field looks like in this case, okay? It's a very highly folded, it's fettuccine that's been stretched out, and you get lots of magnetic energy, but on very small scales. There's no large scale magnetic field being generated. There's no magnetic field like a dipole that emerges from this, it's what we call a fluctuation dynamo or a small dynamo, but it's fast. As far as we can tell, its growth rate stays finite for magnetic Reynolds numbers as large as we can calculate. Okay, so this idea that I just showed you has been known for a long time. It's an example, what I would call, of a Galloway-Proctor flow. Galloway and Proctor were the first people to add time dependence to flows to make them chaotic in this way. This, I think, though, is interesting in that it puts it in a real sphere with real boundary conditions and has a drive mechanism that allows this to be a solution to the Navier-Stokes equation rather than a simple prescribing a very particular flow that doesn't necessarily have a forcing to go with it. Okay, so again, refer to this as a buildable dynamo in that I think I could make a fluid that does this if I could make those boundaries do what I just showed you. Okay? So that's the lesson. That's the lesson I'm trying to give.
What's the Prandtl number for this?
Well, it's the fluid Reynolds number is 50 or something. It's a very high. It's a very high. Once you set the flow, the Prandtl number varies throughout this. So it probably goes from something which is like 5 to enormous. Right? The fluid Reynolds number is fixed, so these dynamos exist way up. And as you go up, this thing gets more and more stretched out, more and more ribbons and so forth. Okay?
How do you define Yarn setup?
Yeah, so again, what we do is we solve the Navier-Stokes equation, and we did it in a time-dependent fashion here. And we specified the fluid Reynolds number in the Navier-Stokes equation that we were solving. And then we varied the amplitude of the sloshing term. So, and this is, I don't have it up here, but it's RE of 100. It's small. RE of 100. RE of 100. RM needs to be big. Yeah. Yes, and so in the end, you can solve this in 2 dimensions using Fluke series analysis, and that's what we did. So you can go to much higher. It's still a 2D problem in that sense. Okay. Well, this is a periodic flow. The flow is periodic. Everything about this flow, it's chaotic for sure, but it's very much periodic. It starts in one phase and goes, you know. This is it. Yes. Yes. Okay. Good. So that's a fast dynamo, and it's in principle a buildable dynamo. Yeah. Yes. Yes. I should give you the reference, and you can. It's a PRL from 2 years ago, and we plot the power spectrum. It's small scale. It doesn't have a large scale component, and I don't remember. Yes, yes, yes. Okay. So I think if you ask most people now, most theorists, they would say that the small scale dynamo is basically understood. You simply have a chaotic flow, and if you make the conductivity high enough that you'll end up with magnetic turbulence on small scales. That's a relatively straightforward problem. The details matter a little bit. So for example, if the fluid Reynolds number is less than the magnetic Reynolds number, the ratio of these two is the Prandtl number. If you make the Prandtl number big, you end up with velocity fields which are smooth and magnetic energy which is developing on smaller scales. The converse is also possible. And so this is kind of the regime where galaxies might operate. In liquid metals or stars, you have the velocity field being very rough and turbulent on the scales of the magnetic field which are present. And so these two limits kind of matter. Okay. So we have small versus large scale. That is, do I have magnetic turbulence or do I have some net flux that emerges from the system? I also have this idea of slow versus fast. Slow dynamos operate at moderate RM, maybe even low RM. Fast dynamos are independent of the resistivity, and they exist even as RM becomes fast, very large. So astrophysical dynamos almost certainly require that they be fast. They're almost always turbulent, but you usually see some sign of large-scale flux being generated. Some large-scale field is usually observed. So on this, and I'll talk about systems in a bit. But the point is, in order to understand astrophysical objects, we need to understand large-scale generation of flux and not the small-scale dynamo. That's not enough. In fact, that's the big conundrum in astrophysical theory these days, is somehow developing a theory for a fast, large-scale dynamo. We don't yet have a good working theory for that. Okay? But you can ask, how does nature do it? I'm not sure we understand exactly, and I'll show you part of that. But we have ideas, and maybe this is a little bit of review, but I'm going to review it from the point of view that these are things we can look for in the lab also. So the standard model for astrophysical dynamos is basically you start with this first step, which is the toroidal generation of toroidal flux from differential rotation. And so this is very, very efficient at stretching out some weak poloidal field into a very strong toroidal field. And this is probably where most of the energy comes from. But this isn't a dynamo because this field doesn't reinforce the initial field that you started with. So you need some additional step. And there was a long period between this era, the dark ages of dynamo theory, in which we were proving that dynamos don't work. The sort of solution came out in the mid-50s. The first person to sort of figure this out was Eugene Parker, and he was looking at models for the solar dynamo, and his idea was that how do I somehow coax this east-west field back into a little bit that can reinforce the north-south field. And his idea was to introduce this alpha effect. And I know you've heard things about this, but the idea is if I have some helical convection, so upwellings that are affected by a Coriolis force, you're going to twist that field line. And if you do it in just the right way, if you have enough of these turbulent eddies doing this, on average, you can end up with a magnetic field which is, well, this got messed up. You come up with a magnetic field which in the poloidal plane looks something like this in the upper hemisphere and something like this in the lower hemisphere. And some sort of reconnection is needed to take this topology and allow it to turn into a large-scale poloidal field like this. So this idea was, I think you've heard about all this, so I won't go into it in too much detail, but you've heard about mean field electrodynamics. And the thing I'd like to concentrate on is that the mean field electrodynamics, you decompose everything into mean fields and so forth. You're left with transport of current, the large-scale current, being governed by a turbulent EMF. This is the thing which is fluctuating the small-scale fluctuations of the velocity field and the magnetic field, giving rise to some average current. So correlations in this quantity can give rise to transport of current. And we think this transport of current can be closed with some transport coefficients, if you will, that we think about as an alpha and a beta term. The alpha term has to do with flow helicity, those types of things that we were talking about. But whenever you have that, there's also almost certainly a turbulent resistivity that comes along for the ride. So I think you've heard about the beta effect as well?
No, not yet.
Nobody's mentioned the beta effect. That's like even more important. I see. So in the typical theories which go through the calculating how these mean field EMFs might develop. If you have a velocity fluctuation which is characteristic of the turbulence, and you put in an induced magnetic field which has to do with a large-scale magnetic field being advected, pushed around by the small-scale velocity field, and you close it, assuming you know what the turbulence is, you can show that in some limits, if everything is homogeneous and isotropic, that the EMF, the turbulent EMF to leading order, will have two terms. One that goes like the magnetic field. This is the generation of current in the direction of the magnetic field. This is the alpha effect. And the other is an EMF which actually opposes the local current, whatever that happens to be. This beta effect is extraordinarily robust. It doesn't require anything like helicity. It just requires that you have some eddies that are moving flux around. In essence, it works like an enhancement to the resistivity. It acts like an enhanced turbulent diffusion that diffuses the average magnetic field more effectively. And I'll come back to this because we've actually measured this quantity directly in laboratory experiments, and it appears to be probably the dominant effect in the liquid metal experiments that we were doing, at least at Wisconsin. Okay, so I'll come to that. Yes. Okay. Okay. So that's kind of how astrophysics does it, maybe. Let's look at some systems and see where things sit. So here's the Earth. It's probably a slow dynamo. It has a modest magnetic Reynolds number. I'm not even sure what the current status of magnetic Reynolds numbers. What's the magnetic Reynolds number in the Earth these days? It's gone up a little bit? Okay, so it's gone up a little bit. We do know that there are some turbulence properties. You've heard about those. I think those have been reviewed. So you've seen probably these movies that Andy's produced. So if we look at the radiomagnetic field from the core mantle boundary over time, he can reconstruct what the magnetic field does versus time, and we see it's dynamic. It has a high order spatial structure. There's some turbulence very much present. It's a turbulent system. If you look at stars, we know there are magnetic fields. It's easy to visualize them, as we were shown this morning. You talked a little bit about the solar cycle, so I won't go into that so much. I'll skip over that, but I will mention that the magnetic Reynolds number for the sun is starting to be large. Okay, and this is telling us something about whether or not a slow dynamo might work. It's almost impossible to imagine something like a slow dynamo being effective in the sun. Okay, so I'll just skip that. The sun very much has a large-scale magnetic field for some part of the time, especially in the quiet periods. So this is the east-west. This is the average of the magnetic field observed on the surface by satellites. If you average in the east-west direction and compute the mean, you get a strong field out at the pole at the bottom and in at the pole at the top during the quiet phase. It reverses every 11 years. You very much have a dipolar field during this phase. Okay? It's not very strong, only tens of Gauss. Okay? But it exists. These things here, which are sort of the sunspots which are emerging, are probably representative of a toroidal magnetic field deep inside the sun that's quite strong, periodically emerging through the surface. So it's also representative of a large-scale magnetic field. Simultaneously with that large-scale field, which is present, we observe it, there's a continual they call it a magnetic carpet, of magnetic field produced at the granule level on the surface of the sun that's also creating magnetic field. And this magnetic field is like 100 Gauss on the small scales. It's present, it's a turbulent small scale dynamo that's probably fast, that's bubbling there and is always present even when the large scale, this is present even throughout the solar cycle. So it doesn't seem to come and go. Maybe they're independent of each other, okay? So can we understand the sun using our standard model? Well, some of the ingredients are there. Helioseismology measures the differential rotation inside the sun. So the differential rotation is present down to the tachocline, so magnetic fields can be wrapped up in the east-west direction. There we see the emergence and twist from Joy's law of the fluxes which emerge from the surface. There's definitely an alpha effect of sorts that happens. So there's magnetic field rising and being twisted like this. But all this has to take place in the presence of a very strong, small-scale, fast dynamo. And that'll turn out to be the big conundrum for this case. Okay? So the small-scale dynamo is stronger than the large-scale dynamo. And yet we still think the large-scale dynamo must be there. Now, I don't think probably nobody's talked about this, but I think it's so cool I want to show you. How about other stars? So if we look into the sky and you asked, are there stars, are they magnetized? Can we learn anything about the magnetic fields of distant point sources of light in the sky? I would have said 10 years ago, there's no way I could learn something about the three-dimensional structure of magnetic fields around stars. But it turns out that I would have been wrong. There are beautiful techniques called spectral polarimetry which have been developed. And the idea is if you have a fast rotating star and you have a dark spot that comes towards you, you can measure the Doppler shift of the light, which is the speed. So here the light is coming towards you, and here it's going away from you. So there's a Doppler shift. And if you measure the emission as a function of wavelength, so I have to toggle this. I'm sorry. Okay. If you look at the light that's coming from a distant star, usually the lines are relatively narrow, and most of what you see if the star is very fast rotating is the Doppler shift of the light. So if this side of the star is moving towards you, it's upshifted in frequency, and if it's going away from you, it's downshifted in frequency. Fine. So, and the stuff right in the middle has no shift of frequency. So what you can do is you can measure that Doppler shifted light. And if you have a dark spot, you can see that you could actually determine where that dark spot was and how fast the star is spinning, both from this Doppler shift, but also from a reduction in the emission. Okay? So the intensity would vary. Now if you look at some lines which are sensitive to the magnetic field, so for example, okay, so Zeeman splitting takes a line and it splits it into several different levels, and from the level the polarization of the line, you can determine what the strength of the magnetic field is. Imagine that there was a vector magnetic field over here, and you were looking at the polarization of the light coming towards you. You would see something like this. You would see this polarization varying with time, and you'd know where on the sun it was happening. And from this, you can reconstruct the spherical harmonic content of the magnetic field which sticks out from the stars. Okay? And they're now doing this. So this, for example, is the reconstruction of the magnetic field which is observed on a star and it has structure. You can tell if it's a dipole or a quadrupole or bigger. You can't resolve the very fine structure, but you can learn quite a bit. And I think this is the interesting thing. It's the really fast rotating stars which are the interesting ones. Here's our sun. This is the rotation period in days. Our sun has is a very slow rotator. And here's the magnetic field strength represented in the size of the star of the size of the dot. So our sun has a very weak magnetic field, only tens of Gauss, the dipolar moment. As you decrease the rotation period, you become a faster and faster rotator, and you go to smaller and smaller star size, so it becomes more and more convective. You get these enormous magnetic fields. Kilogauss and a good fraction of a Tesla-like magnetic fields are actually observed in these stars. So there's spectral polarimetry is starting to tell us that the rotation plays an enormous role, and that there are stars out there which are much more magnetic than our own that are worth looking at. Okay. And they almost always are going to have a small-scale dynamo and as well as a large-scale dynamo. Okay. We know galaxies are magnetized. So, and this has been talked about. The magnetic Reynolds number in galaxies is enormous. It has to be a fast dynamo. There's definitely large-scale magnetic field present. You observe that in the Faraday rotation. We see it for our own Milky Way. We can measure in the Milky Way at some 4 Gauss or so. From the synchrotron emission level, okay, Faraday rotation can tell us the strength of the large-scale magnetic field. So in some average sense, the Faraday rotation of, say, a pulsar that's emitting light coming through this galaxy tells us how strong the magnetic field is on the largest scale. If we look at the strength of the synchrotron emission that's present, we can come up with the magnitude of the total magnetic field, which might not be the same as the large-scale magnetic field. This is now being studied, and what we find is that the total field, this is a collection of galaxies. This is showing that the total magnetic field strength from the synchrotron emission measurement is sort of 15 to 20 Gauss, okay? The Faraday rotation shows average fields of only 4 Gauss or so. This is very suggestive that galaxies are dominated by small-scale magnetic fields, which are sort of a factor of 4 times bigger than the large-scale magnetic field which exists. So again, we must have a fast dynamo. There's a large-scale dynamo because we observe this great structure, the spiral rings and so forth. But at the same time, there's almost certainly a very strong small-scale dynamo working. Okay? Here's another fact that might be interesting. All these systems kind of come into some thermodynamic equilibrium in a sense. This is recent work from a postdoc at Wisconsin where they measured the synchrotron emission to measure the strength of the magnetic field, the plasma emission to calculate the pressure. They're basically in equilibrium. Betas of order 1 for this. The pressure is roughly equal to the magnetic energy. At the same time, they were able to infer the local velocities. And this is in rough equipartition with the turbulent flow. These basically are the same order of magnitude. And if you look at these, they're in rough equipartition with the cosmic ray energy density. The same amount of energy density is present in all of these fields. There's something magical happening there. Okay. So, does an alpha omega model work for the galaxy? Yes, probably. You've looked at super bubbles expanding, giving an alpha effect. The differential rotation in the galactic disk gives the windup. One could write down an alpha omega dynamo, which works pretty well. You need an alpha effect that works. And this is the trouble. I'm not going to show you all the data for this, but most of the simulations that try and investigate an alpha effect in the presence of a strong small-scale dynamo get a most annoying effect, which is that the alpha effect turns off and basically becomes unimportant for very, very strong, small values of the magnetic field. There's a quenching effect, which means that if there's an alpha effect, it goes away the moment there's a tiny magnetic field. So these scalings, for example, this is a scaling which has the magnetic Reynolds number times the strength of the magnetic field. This alpha effect drops off as the magnetic Reynolds number, which in the galaxy is 10 to the 14, times the strength of the magnetic field. It doesn't take anything at all to turn the alpha effect off. And there appears to be an incompatibility in theory between an alpha effect and the small scale dynamo, which almost certainly has to be present in all of these systems. So studying these things could be very important. Okay? So that's what I have to say about, again, I'm trying to give you a sense of what I'm looking at as an experimentalist in these systems. So, experiments. In MHD, Fermi once said, you shouldn't believe the product of a long and complicated piece of mathematics if it's unsupported by observation. And observation is part of the story. I would say experiment is the most important part of the story. Another way of looking at this might be something like this. We're looking at systems which you might roughly characterize in terms of magnetic Reynolds number on one axis and a fluid Reynolds number on the other axis. The sun, is up here. It's very turbulent, has a big magnetic Reynolds number. The Earth might be somewhere here. Liquid sodium experiments can almost match the properties of the Earth. Turns out simulations have a very hard time overlapping with what sodium experiments can do. Okay, they can't simulate, for example, the high level of turbulence, which is almost certainly present in liquid metal experiments. Plasma experiments might have that possibility. So another reason for doing experiments is that we might actually be able to validate some of the codes that we use for predicting how these astrophysical systems behave. So this code validation activity allows us to test our understanding of the physics models that go into them that are then used for predicting what happens in astrophysics. Okay, so dynamo experiments, if we're going to do these, they require some magnetic Reynolds number. They need to be flow dominated. This is a new regime for plasma experiments. We'd like to be able to control the fluid Reynolds number. Plasmas are very challenging. They're difficult to stir. And you need some confinement to allow the plasma to become hot, as I mentioned. And normally, this is done with a strong magnetic field. The tokamaks have strong magnetic fields. And for this reason, it didn't seem appropriate to start with plasmas, although I think in the end it's a good idea. We started with liquid metals. It's very easy to confine liquid metal. You just build a bucket, you pour the liquid metal in, and it's confined. They're easy to stir. You can use propellers. But we have this problem that the fluid Reynolds number is always enormous. These are very, very turbulent systems. If you want the magnetic Reynolds number to be a fixed, the ratio between these two is fixed to be something like 10 to the 5th. Okay? That's how liquid metals, they always have a much bigger fluid Reynolds number than magnetic Reynolds number. And this turbulent scaling for the power required to reach a certain magnetic Reynolds number is very unfortunate. So the power required goes as the cube of the magnetic Reynolds number in turbulent systems. We work extraordinarily hard to accumulate enough sodium. We pay a lot of money. We build a big lab to hold sodium. We put large motors on, and we get 100 kilowatts of power, maybe giving us a magnetic Reynolds number of 100. Imagine trying to go to a regime where fast dynamos existed, like 1,000 or higher. You would need 100 megawatts in the lab to do that. And that's just not going to happen. And so it's impossible in these systems to go there. Okay? And this is in part because these systems have this Prandtl number, which is in this regime. Nonetheless, the liquid sodium experiments inform us about things like, well, you'll see. So This is an experiment we have at the University of Wisconsin. It's a 1 meter diameter sphere. It's filled with liquid sodium. The sodium sits in a tank. We fill the sphere with sodium when we're doing the experiments. We have 2 motors, one on each side, that spin the propellers like I showed you, right? And we had about 150 kilowatts. We were able to get up to a magnetic Reynolds number of about 100. And when we designed the experiment, we thought, this is the flow we would like, okay? Yeah? The main thing that's different between a liquid metal and a plasma in terms of charges is that the collisions between the ions and the electrons which make up the metal are extraordinarily frequent. The mean free path for collisions is tiny, and so the electrons, which are actually, their conductivity is determined by some quantum mechanical wave function that tries to propagate through the ions which are flowing, that is very different than in a plasma where the mean free path can be long. Otherwise, they're the same. Plasma is more like a gas in that it's highly compressible, so its equation of state is different. These are very much, a liquid is a very particular state of matter that differs from a gas. So one's a hot gas, one's a hot liquid. It's the collisionality which is much higher. But you can definitely think about a liquid metal as being electrons flowing through ions. Yeah, a factor of a third of the sound speed. No.